So Avishay will tell us today about Fourier spectrum of Boolean functions.
Thanks. Okay, so this talk will be more like a survey talk. I will discuss several connections between Fourier-tails and switching lemmas and learning and several other stuff. And I will mention a few specific examples towards the second part of the talk. So we are talking about Boolean functions. And what is a Boolean function? So this is a function from plus minus 1 to the n to plus minus 1. So you will see why we insist of plus minus 1 instead of 0, 1 in a minute. But if you want, minus 1 represents true, and plus 1 represents false. So let's give a few examples of Boolean functions that you should keep in mind. So one is the parity function. So in this notation, this is simply the product of xi's. Okay, so if you think about it, you count how many true bits you have, and you take it modulo 2. Right, so this is parity. Another Boolean function that you should keep in mind is the majority function. So this is, we just sum the bits, sum the xi's. And if it is greater or equal than 0, we return 1, and otherwise we return minus 1. So this you can think of as like some kind of voting mechanism. Right? Each one has an opinion, if it's positive or negative, and you take the majority opinion.
So it's the sign of the function.
Yeah. So this is majority. And simply the dictator. I take only one variable and output it. So I just wanted to give this example to demonstrate that we don't need to depend on all the inputs. Okay, so this is the dictator function. So what is the Fourier transform? This is the unique multilinear polynomial that agrees with the Boolean function. Okay, so just this definition requires a proof. First, that there exists such a polynomial that is unique. So, but let's write it down. So the Fourier transform is a unique multilinear polynomial that agrees with the function f on plus minus 1 to the n.
The coefficient of what is normally called the Fourier transform.
Okay.
The coefficient.
So how do you call it the polynomial? I don't know. Okay.
The multilinear extension of
Okay.
the Boolean function.
Okay. So an inner product between Boolean functions. So for f and g, both of them are Boolean functions. Takes the inner product to be the expectation over all inputs when I'm taking a uniform random x of fx times gx. Okay, so if they are both Boolean functions, this is a number between minus 1 and 1. And it measures how much does this function agree. If they agree on half plus epsilon, this will be, I think, 2 epsilon. Okay? So this is a correlation between f and g. So now, once I have an inner product, I can find an orthonormal basis with respect to this inner product. And this orthonormal basis is the basis of characters. So I have 2 to the n characters. One corresponding to each subset of the numbers between 1 till n, And these characters are simply the monomials. Okay, so it is the product of xi where I is in the set S. Okay. So it is a it is not hard to check that indeed for any s different than t, the inner product of xs and xt is 0. And the inner product of xs with itself is 1 because, right, the expectation of any Boolean function squared is 1 because it is 2 plus minus 1. So this is an orthonormal basis. We have 2 to the n of them, so this is indeed a basis. Okay, because the space of functions from plus minus 1 to the n to the reals is a linear space of dimension 2 to the n. So we found enough linearly independent functions there. That means that this is a basis. So we can write uniquely any Boolean function f in this basis. So we write it in this basis. We have some coefficient, and we have the character. All right. So this is the polynomial, and this is a number in R. Okay. And I'm just writing it down. And I'm sure most of you have seen it, but I just want to set up notation and to do things slow. Okay, so once we have this, we have a few very nice observations. So first, how can we calculate this coefficient, the Fourier coefficient? So we can simply take the inner product of the function with the character, right? Since these are orthonormal, if I express, I will write f as the sum of these. Everything is 0 except for the s coefficient, and then I get that this is equals this. Another very nice equality is what is called Plancherel. So if I want to measure the inner product between two Boolean functions, so again, I can write each one of them in the Fourier expansion, and then I get that everything cancels out except for matching coefficients. And the special case is when f equals g, in which sum of squares equals this thing. And what is this? This is the expectation of fx squared. And in case that f is Boolean, this is 1. Right? So we get that the sum of squares is 1, and the correlation is the sum of products. Okay, so maybe let's see an example of how the Fourier expansion look on, let's say, on these things. So first, for the party function, it is already given. Okay, this is the Fourier expansion. It is just this monomial. For the dictator, it is also given. This is this thing. For the majority, it is slightly more complicated. So let's write it down for the majority on 3 elements. Okay, so I want to check if at least 2 of them are 1. So it turns out that this equals okay, this equals this polynomial. You can check. For example, take all of them to be 1. You get half plus half plus half minus half. So you get 1. Check any other possibility, and you will see that it agrees with the function. And you can see that the sum of squares is 1 here. And each coefficient measures the correlation between the majority function with this character. Okay. So what's nice about this Perceval identity is that it naturally defines a probability distribution over sets. Okay? So since the sum of squares equals 1, I can define the distribution with respect to a Boolean function. Okay? So each function has a different coefficient. So this distribution, we sample a set S with probability fs squared. And now we may ask several questions with respect to this distribution. So one thing that we can ask is, what is the expected size of the set? Okay. So this is just the sum of squares times the size of the set, right? So same thing, and this is usually denoted by the influence of the function. Okay, there is also a combinatorial way to define this influence, and it matches this thing. We will later discuss it. And another thing that we will be interested, which is the main topic of this talk, is the Fourier weights and the Fourier-tails. So what is the Fourier weight? So for every number k between 1 till n, or 0 till n, we just take the sum of squares for sets of size k. So we ask how much mass do we have on this set. So you can think of it as a probability distribution. How much mass do we have, or the probability that S, according to this thing, its size equals k. Right? Obviously, if we know this thing, we could calculate this thing, right? Because it just depends on the. Okay, this equals the sum of weights level k times k. So this will be sufficient to compute this, and the tail is simply when I'm taking at least k. Okay, so it's the same thing.
And this influence is the same as the influence.
Yeah, it's the average. That's called the average. Yeah, it's the usual influence.
The total influence or the average sensitivity. Yes. Yeah. So. Yeah, so maybe let's see the influence defined a bit differently. So for every I from 1 till n, I want to define the influence of this variable on the output of the function. Okay, so I want to define this thing. Okay, to do this, I first define the derivative with respect to I. Okay, so derivative of this will be simply the derivative of the polynomial with respect to the variable xi. So you can write it as, so all the sets that remain are the sets that contains I, and I take all the j's in S minus I. Right, this is the formal derivative, and it turns out this equals exactly the value of f on x when I substitute xi with 1, minus the value of f on x when I substitute xi with minus 1, and I divide by 2. So you can see this is, because this is multilinear. Yeah, I mean here for a certain x. Okay, so the derivative of f is a new function, not Boolean now. So this simply takes the value of f on x when I replace xi with 1 minus 1. So this is the same as the derivative, right? Because it's multilinear, so it doesn't really matter which. I usually take delta, right? I take f on 0 and delta, but it doesn't really matter. Okay, so what is the expected thing of this squared? So first, what does this mean? The derivative squared, it just measures if the ith coordinate is influential for the given input x, right? If both of them are equal, it means that it doesn't matter if I change xi. If they are not equal, then it is either +1 or -1, but then if I take it to be squared, then it is +1. So it just measures what's the probability that the ith coordinate is influenced. So this is, again, by Parseval. What does this equals? It's the sum of squares. Right? And now if I take, so this is called the ith influence, and take the sum of them, so this is simply sum over I, sum over S containing I, this thing, right? So now I go over all S's and I ask how many times do I count each set. So I count it exactly the cardinality of S times, right? Because I have here a lot of I's. Okay, so you see that like this is the influence is has a very combinatorial interpretation. However, it has a nice expression in the Fourier basis. Okay.
I think it's good just to advertise the big question of Fourier analysis of Boolean functions. Just what can we say about these distributions that are special? So every Boolean function gives a probability distribution.
Yes. Right.
Not all distributions. What can we say
That's
about
true.
them in this field of?
Yeah. So if we just look on this expression, the question is how do we capture the Booleanity of the function, the fact that each value is ±1. So we can capture it in a maybe ugly way, but okay, we can just take the inverse Fourier transform and then say that everything is ±1. But can we say something more simple in this basis that captures Booleanity? And we will demonstrate.
No, there's no conjecture. It's just that people keep finding consequences of the Booleanity, and you'll see some examples here. They just find more and more properties of this distribution, like bounds on tails and blah blah.
Yes. So, for example, one conjecture is entropy influence conjecture that says that you can define the entropy of this distribution, and the conjecture is that the entropy is bounded by a constant times the influence. Okay, so this is not true for non-Boolean function, but for all we know, it may be true for Boolean function.
But the basic, I mean, this is determine the dimension is 4, right? I mean, the dimension is. But you have a discrete set inside the.
Yeah, you have all the parity function. All the parity functions are Boolean function, and they span everything, right? But yes. Okay, so now I want to state the property of Boolean function which I will be interested in, and that is that it has exponentially small Fourier-tails. So I will have some parameter t, which will be between 0 and n. And I will want that for any k, the weight at level at least k is at most e to the minus k over t. So I have some threshold level t, okay? And starting from this level, the tail decreases exponentially fast, okay? So you can look at the picture. So I have this k, and here I have the Fourier weight at level k. So for any Boolean function, it describes the distribution over these layers, right? I have n+1 layers, and each one sums the coefficient of the sets of size exactly k. So this property tells us that I have some level t. I don't know much before it, but starting from this level, I know that it increases exponentially fast. So for example, if I take here, I don't know, t times log 1 over epsilon, the weight is at most epsilon here. Okay, so this is a property of Boolean function that I call exponentially small Fourier-tails with parameter t. And I want to demonstrate that it happens for many nice examples of families of Boolean function, and then I want to describe how can we prove such a theorem and the equivalence of this property and consequences of this property. Okay. If I want to be a little bit more accurate, I want to multiply here by e, because I really don't know what happens before level t. So I don't want to say that it starts to decrease from 0. I want to say that it starts to decrease from t. Okay, but this is, you can ignore that if you want. Okay. So now I want to list classes of Boolean function with this property. Okay, so there are some degenerate cases. For example, all Boolean functions have this property when I take t to be n, because I don't really require anything. I just require that starting from n it decreases, but there is nothing there. And if I take Boolean function whose degree as a polynomial is d, then they also have this property with t equals d, because there is nothing above level d. Okay, but more interesting classes are when you have something above it, but it decreases exponentially fast. And the first example is what is called width W DNFs or CNFs. So what are these objects? So let's show what is a DNF. So it is something that you can write as an OR of ends, where each, okay, so you have some Boolean variables or the negations. And so you have these terms. Each term has at most W variables or the negation, and you have as many terms as you want. Okay, so Hastad, and then later Lineal, Mansour, and Nissan showed that for this class of Boolean function, you have exponentially small Fourier-tails where t equals a constant times w. So there is no dependency on n, and no dependency on the length of the number of clauses. So this is what is called the switching lemma. So the switching lemma describes it in another equivalent form, but then Lineal, Mansour, Nissan deduced from it the Fourier-tails. They translated it into the language of Fourier analysis. Actually, it was one of the first uses of Fourier analysis in theoretical computer science and the study of Boolean functions. Okay, so this is the switching lemma. So the second case is on a generalization of this. So it is what is called AC0 circuits. So here we have two parameters. So we have the size, which is the number of gates. This will be denoted by M, and the depth will be denoted by D. Okay. So what is an AC0 circuit? So again, we have AND and ORs. So we have, let's say, an AND. And each gate is fed by many other gates or inputs. Something like this. And I may have, okay, so I have these gates. On the bottom layer, I have variables with a negation. And on all the other layers, I have AND gates or OR gates. Okay, and this describes the computation. I can propagate values from leaves to roots. Okay, and so a special case is depth 2, which is DNFs or CNFs. But you can define it for any depth. And so what is a depth? It's just the number of layers. In this case, it will be 3. Okay, so it is the number of gates from the input to the output. And the size is simply the number of gates. Okay, so for this kind of thing, we also know exponentially small Fourier-tails. So in the work of Linear Nutsoni-san, they deduce tails which are not not really exponentially small as I define it like this. They did something which is exponentially small in k to the 1 over d. So if you, let's say, exponentially small in, let's say, square root k or something like that. And recently, via work of Hastad and myself, we showed that this holds for t, which is log m to the d minus 1. So if you want to think of certain parameters, so think of m as polynomial in n, and think of d as a constant. So this is like polylogarithmic in n. So it means that this picture looks like this when t is roughly polylog n, which is very, very small. Right, so maybe I will. So I have something like this. So this is how the Fourier spectrum of such circuit looks like. And this involves also a new kind of switching lemma and then Fourier calculations. The third example is of De Morgan formulas. Okay, of size s. They have this property with t equals square root s. And what are De Morgan formulas of size s? So it is pretty similar to this picture with a few changes. So first, I don't have any any demand on the depth. I can have any depth that I want. However, I have two things that I change. So one is that each gate cannot be fed to two other gates, so it can be fed only to one. So this is a tree. Okay, so this is how this tree looks like, and each gate is only fed by two inputs, two other gates. Okay, so this is the Morgan formula. Is a binary tree of AND and OR gates. And I still have variables or the negation on the leaves. And again, the number of gates is the size of the circuit. Okay, so for the Morgan formulas with size S, it is known that there are exponentially small Fourier-tails with parameter t, which is square root of S. So this looks much bigger than this, but this model is much stronger because I have no demand on the depth. I can do things which are more complicated.
Maybe you should say that all results so far are tight.
Yes. Yeah. Yeah, I wanted to say all of them and then to mention. Yeah, all these results are tight, and you can ask yourself, well, what does all these results mean? They mean that you cannot compute the parity function, right? The parity function has all its weight on the nth level. So this means that this thing has exponentially small weight on level, exponentially in n over w, right? And this is exponentially small in n over like polylog n. And this is exponentially small in n over square root s. But in fact, these are tight because you can compute parity if you add width n, and you can compute parity if log m to the d minus 1 is n, and you can compute parity in size n squared with the Morgan formulas. So these results are tight. Okay, and also the fourth result is tight. So the fourth result is about Boolean functions. Wait, I need to say how does this was proved using a completely different technique, a technique of quantum algorithms. And I will mention the connection between quantum algorithms and this thing. But this was a long line of work, and the last one that proved this result was of Reichardt, 2011. Okay. So it seems that like it's a list of things, but each one of them is like a big paper. It's not a simple result. So the last result that I want to mention is Boolean function with maximum sensitivity S. So what is the maximum sensitivity? So this is the sensitivity of f on a point x. I simply count how many neighbors I have on the Boolean cube. With different value, such that fx is not equal to fx I, where I is the same thing, xi is the same thing as x, where I just flip the ith coordinate. All right, so this is the same as like summing over all the derivatives squared. And so the average sensitivity is the total influence, but here we are talking about the maximum sensitivity. Okay, so we are looking at the maximum over all x's of this thing. You can think of it as if you had a graph which is a subgraph of the hypercube, and you connect an edge between two neighbors if they have a different value. Okay, and you ask what is the maximum degree in this graph. Okay, so if this maximum degree is S, so in a joint work with Gopalan, Servideo, and Avi, we show that these functions have exponentially small Fourier-tails with parameter S. Okay, yeah, I want to mention what is equivalent to small tails. This is something which may be more intuitive. So having small tails is equivalent to having a low degree approximation. Okay. So fact, a Boolean. Okay, so a function f has Fourier-tail above level k at most epsilon, if and only if there exists a polynomial p of degree k minus 1 such that the L2 distance between f and p is at most epsilon. So let's show one direction. Let's show that if this holds, then we have a low degree approximator. So simply we can take P to be the truncated Fourier expansion. So we take all the characters up to size k minus 1. Okay. So this is a degree k minus 1 because all these monomials are involved with mod k minus 1 variables. And what is the expected value of fx minus px squared? So this is exactly, yeah, okay. This is, what do I have left when I subtract the 2? I'm left only with the large characters, right? So I'm left only with the sets of size bigger than k. But now from Parseval, I know that this expectation squared is exactly the sum of squares, which is at most epsilon, right? So if I have a small tail, then it means that I have a good approximation by low degree. And this is also if and only if, because this is the best choice that I could do to pick a degree k minus 1 polynomial. You can see this by this calculation. Let's say that I didn't pick it, then I have here maybe some other coefficient for smaller sets, which will contribute more to this sum of squares. So this is the minimizer, and from the fact that this is a minimizer, this is an if and only if statement.
It's in the down, but it's probably good to stress that this approximation is approximation in the L2 norm, and people
Yes.
studied approximations of Boolean functions by polynomials in other norms.
Yes. So yeah, for example, what I mentioned of the quantum algorithm, this is an approximation this gives an approximation with respect to the L infinity norm. So in particular, it gives an approximation with respect to L2 norm. Yeah, and so several norms are considered. Okay, now I want to give you a map of all the connections maybe I will do it here. Okay, yes. Yeah, so basically you can interpret all these results as saying that there is, for any epsilon that you choose, there is a degree t times log 1 over epsilon that epsilon approximates each one of these functions, where t is w here, or log m to the d minus 1 here, or square root s here, or the maximum sensitivity here. Okay? Right, now I want to show how all these relate to other things. So to quantum algorithms. So whenever you have a quantum algorithm for computing the function f with t queries, where query I mean reading an input bit, then this implies L infinity approximation by degree t, which implies exponentially small Fourier-tails with parameter t. So why is that? It is because if I want to make error epsilon, I can repeat this log 1 over epsilon times, and then I could get here an approximation epsilon with degree t times log 1 over epsilon. I will get here the same thing. I will show that this is equivalent to what I call moment bounds with parameter t. So if you recall, the influence was the first moment of the size of the set. And I will talk about higher moments of the size of the set. Okay, so this will be equivalent to this. I will define it in a bit. And all these two will be equivalent to some kind of switching lemma with parameter t, which will tell me how does the Boolean function behave with respect to random restrictions. And I will define it also next and show the equivalence. This also, okay, so we already saw that this is equivalent to being approximated by a low degree polynomial in L2. Okay. Now I want to mention, okay, so now I want to mention some applications. So the fact that you can be approximated by degree t in L infinity means that you can learn the Boolean function under any distribution. So this is called pack learning. It is enough to have this kind of thing, to have a pack learning algorithm which runs in times, I think, something like n to the t. Okay. This thing implies that you have a learning algorithm with respect to the uniform distribution with the same running time n to the t. So this is weaker than this. Okay, if we have this means that we can learn with respect to any distribution. This means that we just can learn with respect to the uniform distribution. It also implies, okay, so here we said that you can be approximated by a degree t polynomial, more or less. So how many monomials we have in degree t? We have roughly n to the t. But in fact, this implies something even stronger. It implies that you can be approximated by a polynomial of sparsity something like t to the t. And if you want some dependency on epsilon, so it's something like this, t to the t to the log 1 over epsilon. Okay, so the number of monomials is much smaller than the trivial bound of the degree, n to the power of the degree. So this also implies better learning under what is called the membership query model, when I can ask the black box for a question and gives me answers. In the L2. This is in L2. Also, yeah. Yes.
It's hard for me to believe you can learn anything under an arbitrary distribution.
Not okay. First of all, it's n to the t, so maybe it's exponential.
Well, so I have to return n to the t different.
So it's not anything. So I'm saying that if you have let's say if you have an L infinity approximation of a Boolean function by degree t, then you can learn this Boolean function without knowing it in time n to the t.
But what is the setup? Do I get to ask?
You get to see random examples distributed according to an unknown distribution, and you need to come up with an hypothesis that it is correct with respect to this distribution. Okay. But here in the uniform model, you just get examples sampled according to the uniform distribution and of x's and f of x. Okay, so yeah, I want to check that I didn't forget anything. Okay, so and one consequences which requires a little bit more is that from such things you can deduce PRGs, but it requires a little bit more. It requires that you're also close to composition and close to projections. So this does not hold. For example, I don't know if this holds for the fourth case, because this class of function is not close to these operations. But you can do it using the Nissan-Wigderson construction. And why is that? So recall that what does it mean to have exponentially small Fourier-tail? It means particularly that parity is a hard function for this class of Boolean functions. So if you have functions that is hard to approximate, the Nissan-Wigderson generator translates it into a pseudo-random generator. So this gives a pseudo-random generator, I think, with seed length something like this. And for several of these classes, you can tailor-made PRGs which get something like O of t, which is better than this thing. But this is not. This is specific to each example. Okay. So I want to tell you a bit more about this thing, and then I will mention maybe some of the applications to learning. But if you have any question about this picture, it's a good time to ask now. Well, this implies this. Okay, so it requires some notation, but it's not difficult to resolve. I mean, simply each query that you do to the input, you increase the degree by 1, more or less. So why does this? Maybe it's easy to see why that this gives a L infinity approximation. So the quantum algorithm should be correct on each input with probability, let's say, 1 minus epsilon. So this translates into something which is correct on each input with probability 1 exception. I'm ignoring a constant factor. Yeah, so this is everything you can replace t with O of t. Okay, maybe it's a good time to take a break. Okay, just to connect the top board with the bottom board. So results 1, 2, and 4 were proven in the language of the switching lemma, which I will mention in a bit. And the third result was proven using the quantum algorithms. Although I think there is a recent proof which uses more classical techniques of Impagliazzo and Cabanets. Okay, so now I want to tell you what are these MBT and SLT, the moment bounds and switching lemma properties, and to tell you a little bit why they are equivalent to the exponentially small Fourier-tails. What conjecture?
What is the widest conjecture about that? The most general conjecture about functions that have small
This is a lot
Okay, so there are some I think related to this, there are two conjectures. So one conjecture is about the maximum sensitivity. So there we believe that there is actually a polynomial that agrees with the function of degree, let's say, s squared. Okay, so we believe that the tails are 0 above some level. We know that for all the results that we said, the results are tight, so we cannot expect to prove something stronger than that. The class of functions that tells this. So, yeah, I'm not sure. I'm not sure.
It would be interesting to find more families.
But for example, you could you could.
Yeah.
So maybe something that sheds some light that this doesn't capture everything. So for example, we said that let's say DNFs and AC0 circuits have this property. However, Li Yang, that was here a few weeks ago, he showed us that there are functions that can be computed by depth, let's say 3, that cannot be approximated by depth 2. In the language of Fourier, we don't really. In the language of exponentially small Fourier-tails, we don't really distinguish between the two. Maybe this is polylog versus log, but this is not a big gap. Okay, he showed an exponential gap. So there are some things that are not captured by this thing. So random function will have most of the weight on level n over 2 or something like that. So they will not have. So these are like very unique functions.
Sure, you didn't discuss monotone functions also there. I don't think those are exponential, but they decay from both time.
Yes, but not. But maybe polynomial. Yeah. So for the majority function, which is monotone, we know that it actually decays from 0. So it starts to decay in the beginning. However, the decay, like the weight at level k, is 1 over k to the 1 over polynomial in k. So you may ask, okay, maybe I can. It doesn't capture the exponentially small Fourier-tails, but maybe I can approximate majority by these kind of functions. And the answer is no. Maybe if I'll have time, and I think that I won't have time, I will show you this. But Yes, I'm not sure. I mean, some of these results are new, so I'm not sure that I have enough time to process all of them and say what do I think about what characterizes this family. But it seems that like for each one of them, it looks like you use different techniques, but actually you can unify all these to this framework. Okay. So I want to define the moment bounds with parameter t. So we call the definition of influence. This was the expected size of the set, right, with respect to the distribution, or the sum of squares times the size of the set. Now I want to define higher moments, and I will define it in a weird way, but I will justify it. So this will be the expectation. The kth moment will be the expectation of S choose K. So maybe a more natural would be to take S to the K, but this will be nicer to work with, and I will show you how this comes out naturally. Okay, so recall that we have this derivative operator, right? Which for a given function, if we apply it, it gives us just the sum of all Fourier characters under coefficients when the character contains I. Okay. So this is the derivative. So now I generalize this derivative to, well, I just take several derivatives. So I have t, which is several coordinates, I1 up till ik. And I take the derivative with respect to I1, and then with respect to I2, till with respect to ik. Okay. So I call this a derivative of the set T, and this equals, okay, so each time we are doing it, we are just taking the sets that contain some coordinates. So in the end, we have all the sets that contain T. So I have this coefficient times everything in S minus T. Right? And another way to write this thing is half times f of x when we plug in xi equals 1 minus f of x when we plug in xi equals minus 1. Right? This was another way to write it. So here it will be the sum over all possibilities to assign variables in T. So we are assigning all the variables in T some value Z, and we multiply by Zi, where I is in T. Okay. So recall that the influence was also the sum of the derivative squared, the expectation of the sum of the derivative squared. So now we will take the sum of this derivative squared when we sum over all sets of size k. Okay, so for one set we have this equals simply this thing. And when we sum over all sets, what do we get? So each set S is counted. Okay, we're going over all sets of size k. Each set S is counted here. S choose k times, right? I can choose any subset of size k, and it gives me one application of it. So I have this thing, and S choose k. Okay, so this is why this is a natural definition. And the moment bound with parameter t, some Boolean function has this property if and only if for any k, the kth influence is at most t to the k. All right. So the first thing is to show that the exponentially small Fourier-tails imply moment bound. But this is a pretty straightforward calculation, right? If I want to compute this thing, and I know how these tails behave, I know that level, I can go over all sets S of size L. I can go here over L from k to n. I can take the Fourier weight at level L times L choose k. Right, this exactly equals this thing. And since I know the tails of the weights, I can plug it in and I get this bound. Okay, so I won't show it, but it's really simple calculation. Okay, maybe to be more careful, let's write it something like this. So maybe I have a constant times t here. And the next thing I want to do is to define the switching lemma property and to define and to show that it is deduced by the moment bound. So when we talk about switching lemmas, we talk about random restriction. So recall that we have this Boolean function defined on n bits. So in order to better understand this function, it is very useful to look at a sub-function of it. So what are we doing? We are picking some of the coordinates and picking constant to them. And we are fixing this coordinate to this constant, and the rest of the coordinate we keep alive. So let's, for example, pick for the first coordinate the constant 1, -1 for the second 1, x3, x4. And we will apply these things, and we will show that there is a very nice connection between the Fourier expansion of this function and the Fourier expansion of this function. And in fact, it will be, in some cases, it is much easier to analyze this function and then to deduce from it tails about this function. This is what is done usually in the switching lemma. We understand what happens here, and then linear notation sum translated it into Fourier-tails on the original function.
Mati has a way of saying what these random restrictions are that are obvious. That is obvious. It's the same description, but it's not some people.
Okay.
You just focus your attention on a random subcube of the Boolean cube and look at how the function looks like that.
Yes. Yes.
For the fixing of coordinates, it's just specifying which subcube you are looking at.
Exactly. Yes. Okay, and we in particular will be interested in distribution of restrictions that is called the p-random restriction. So for each coordinate, for each I from 1 till n, with probability p, we keep xi alive. With probability 1 minus p over 2, we fix xi to be 1. And with probability 1 minus p over 2, we fix it to minus 1. So roughly, we are keeping p fraction of the variables alive. And what we'll want to show is that the function becomes very simple under this random restriction. So the switching lemma property with parameter t says the following. Says that the probability. Okay, so we denote this kind of this restriction. You can think of it as a string in minus 1, 1 star to the n. Okay, so for every variable, so the string will be minus 1, 1 star, star, 1 star. Okay, so if we keep it alive, we put star there, and if we fix it, we put minus 1 or 1. And the restricted function is simply this sub-function, okay? Just when we plug in constant instead of variables. So we ask what is the probability under a random restriction distributed according to this thing, that the degree of the restricted function, so we denote it by this. This is the restricted function. Equals d. Well, let's write greater or equal d. Is smaller or equal than some constant times p times t to the d. Okay, so you have. Okay, so this is with parameter p, right? The parameter p tells you how many variables you keep alive. So you want this probability to be some constant times p times t, where t is this specified here, to the power of d. For example, for with WDNFs, so this is a constant times p times w to the d. And this is the original switching lemma, more or less, except that Hassad proved it with something even stronger than that. He proved it with decision tree, which is always bigger than the degree. So he showed something slightly stronger than that, but for this connection, it is we need this notion.
So p is chosen usually to be like 1 over 10.
Yeah, in order for this to be something meaningful, right? So this is a probability, so you want it to be much smaller than 1, right? So you pick p to be 1 over some constant times t, such that this will be a small constant to the power of d. So what does it tell us? It tells us that under random restriction, there is no weight above level d with very high probability. The probability that there is some weight is exponentially small in d. Okay, so this is a much stronger notion than exponentially small Fourier-tails. It tells us that there is nothing there. However, it is equivalent to it. Because why? Because we are looking at a sub-function. We are not looking at the original function. Okay, so now I want to show that moments bounds with parameter t implies switching lemma with parameter t. Okay, I will do it here. So let's look at one example. So the parity function, right? So this is a simple function. What happens to this function when we apply random restriction, p-random restriction? What do we get? More or less. The parity function of how many variables? Roughly p times n, right? We are keeping each variable alive with probability p. So we are, after random restriction, or p random restriction, we are left with a parity, or maybe it's negation, on more or less p times n variables. So and how does this how does the weights of this function look like? You have weight of 1 on n and 0 anywhere else. And the same goes here for this parity function. So it means that if you look at this picture, right? So here you had, so this is the weight, and this is k. So here you have just weight 1 here and 0 everywhere else. This is a parity function. And after the random restriction, so the number of variables behaves like a binomial random variables, like a bell-shaped thing around p times n. So the expected weight at level k of the restricted function, this is a random function because it depends on a random restriction. So we may ask what is the expected weight of this function. It behaves roughly like this. So in this picture, okay, so this is true for the parity function. It is pretty easy to see it. But it turns out that this is the case for all Boolean functions. If you know the spectrum, so let's say the spectrum is, I don't know, something like this, then and this is some t, then it moves to something like this, around pt. So everything is shrunk by a factor of p. And to be more precise, so this is a lemma by Lineal, Malsu, and Nissan. So the expected weight at level k of the restricted function, okay, equals the weight of the original function times the probability that a binomial experiment with L experiment and probability of success P equals K. Okay, so this is if we have just a parity function, it is obvious, and it is also not that difficult to show this lemma. So more or less, you can think of it as this way. In order to describe this this distribution, you can first sample according to the original distribution, and then keep. So you sample a set of size, let's say of size L, and then you keep each variable in the set with probability P. Okay, so more or less you are left with the number of things that you had times P. Okay, so this tells us that everything is shrinking by a factor of P. So why does this imply the switching lemma property? Okay, so let's write it. Okay, maybe I will continue it here. So let's write it down. What does this mean? This is the weighted level L times L choose K times P to the K times 1 minus P to the L minus K. Right? This is equality, and this is at most. So now I want to remove this thing. So this is at most P to the K. I can take it out of the sum. Sigma the weighted level L times L choose K. Right? And what is this? This is exactly the moment, the kth moment. Right? So this is exactly P to the K times the kth moment. So just by this lemma of linear Mortzun and Nissan, we get a very nice upper bound for the expected weight at level K. We get that it is P to the K times the kth influence, the kth moment. And if we assume the MBT, then this is at most P to the K, T to the K, right? This is exactly the assumption that we had. However, we said something about the degree, not about this thing. So we need another thing. We need a lower bound on this quantity that involves a degree. Okay. So this is at least the probability that the degree equals K. That the degree of the restricted function equals K times the expected weight condition on this. Right? Because this equals actually the sum of all possible degrees of the probability that degree equals something times the the conditional expectation. Okay, and now I want to use something about Booleanity of the function. So it is a simple fact that if you have a function and it's the Boolean function and it is of degree K, then every Fourier coefficient is an integer divided by 2 to the K, or 2 to the degree. Okay, so every Fourier coefficient looks of this form. You can prove it by induction. It is a simple fact. So what does this mean? It means if we know that the degree equals K, it means that there exists some non-zero of degree K. However, the minimal value it could attain is 1 over 2 to the K. Right? So this means that this is at least, so the square is at least 1 over 4 to the K. And then we can take this lower bound and this upper bound and get from both of them that the probability that the degree equals K is at most 4 to the K, P to the K, T to the K. So we get from the moment bounds, we get the switching lemma property. And I want to mention that from the switching lemma property, okay, so this finishes this derivation. I want to mention that also from the switching lemma you can deduce exponentially small Fourier-tails. This is also simple. This was done by Lineal Mansour and Nissan. So Hastad proved the switching lemma for DNFs and for IC0, and they deduced from it exponentially small Fourier-tails. Okay, so maybe now it's a good time to move to the applications. So So the first application that I want to mention is the fact that you can learn under a uniform distribution. Okay, so this is again the result of linear Manzoni-Nissan. Okay. So we know that if we have exponentially small Fourier-tails, we are approximated by by degree. Okay, so I want to say epsilon approximated by degree t log 1 over epsilon in L2. Okay, so in particular, most of the Fourier mass lie on the first t log 1 over epsilon layers in the Fourier expansion. So the algorithm is pretty straightforward. So we are going over all sets of such size. For all sets S of size at most t log 1 over epsilon. We estimate the Fourier coefficient of the set. So we don't know it exactly, so we'll get some kind of approximation of this Fourier coefficient. So let's call it f tilde of S. And in the end, what we need to output some Boolean function. So we output the sign going over all sets of size at most t log 1 over epsilon. Of this estimate times the character. Okay, so if here we would output just the true Fourier coefficient, then we know that this approximates the function, and this means also that the sign approximates the function. The sign agrees with the function with probability 1 minus epsilon. Okay, so this is not a difficult exercise. So the only thing that we need to worry about is, can we estimate it in a good way? And the reason that we can do it is just by the definition of the Fourier coefficient. So we recall that what is a Fourier coefficient? It is the correlation of the function with the parity function. Right? This is the expectation of this thing when we go over all x's, right? But these numbers are plus or minus 1s, right? So if we have samples, random samples of these numbers, we can estimate this with very high accuracy just by taking like the average of all samples that we saw, right? And then we use the Chernoff-Bow to argue that this is concentrated around the right value, right? So more or less the number. Okay, so we need the number of to estimate each one of them. I think we need like polynomial in the accuracies that we want. And the accuracies that we want is more or less the number of sets that we are looking at. So all in all, we get that this works in time, which is polynomial, in the number of sets, which is polynomial in n to the t log 1 over epsilon. Okay, this is the running time of this algorithm. Okay, so for example, let's check what it gives for DNF. So for DNFs, it gives n to the w. Later, Mansour showed that you can do it with w to the w, but this was not under random examples that you see, but under the models that you could ask for a query. And this follows by the fact that, the fact that actually you are approximated by a much sparse polynomial than just taking all the possible monomials. Okay. Okay, so the second application that I want to mention is
It's a slightly different problem to do DNFs.
right.
Polynomial size DNFs
Right.
in polynomial time.
Yes. So here, the sparsity is t to the O of t, and it could be possible that here you could get something like 2 to the O of t, and some dependency on epsilon. And if this is correct, then this solves both the entropy inference conjecture and Mansour conjecture. So the entropy inference I already mentioned earlier, but in Mansour conjecture says that if you have a polynomial size DNF, then it is concentrated on polynomial number of Fourier coefficient. So most of the mass sits on polynomial number of Fourier coefficient, and he managed to show it with n to the log n. However, there is no counterexample, so it could be the case that there is a polynomial number, and this is implied by the Fourier entropy inference conjecture. Mansour conjecture is implied by that. Yeah, so this is one open problem here. Can we get this? Okay. Now I want to tell you about an application to shrinkage of De Morgan formulas.
You're shrinking the size of your font also.
Ah, sorry. Yeah.
Okay.
Yeah. Okay. I will try. Okay, so recall what is the De Morgan formula. So we had this tree. Something like this. So we have a tree. We call it a formula. The size of it is just the number of gates in this tree. So we denote it by S. And we mentioned that from quantum algorithms, these kind of, okay, so this represents a Boolean function, and this kind of Boolean function has a exponentially small Fourier-tails with parameter square root S. Okay, so the tails decay exponentially fast, starting from level square root S. And from this, I want to prove that under P random restriction, this shrink by a factor of P squared. So what we will do, for each variable, we will keep it alive with probability P. And with probability 1 minus P, we fix it to a random constant. So more or less, we are left with P times N variables. However, because of cancellations, for example, if this variable will be false, then this gate is killed, right? So by this kind of simplification, actually more nodes in the formula are killed by this random restriction. And what happens is that the expected size under random restriction with parameter p. So the result is that this is p squared times the original size, okay, maybe plus O of 1. And I want to show how this implies this.
Maybe you should mention that this is the first time random restrictions were implemented in the 1960s in Russia by Skłodowska, who used this idea to put
Yes.
the low bound of 10 to the 3 halves on the model formula for parity. And what she got is p to the 3 halves instead of 2, which is a very simple. That's a very simple. Long before random restrictions appeared for AC0 and so on.
Yes. Yeah. So Skłodowska showed this with 3/2, and then this exponent was improved to 1.55 and 1.63, and eventually Assad showed it with 2, but there was some logarithmic terms, and using this result you could get rid of the logarithmic terms. So there is not much to do. We have done most of the preparation in order to prove this thing. So recall that if we assume this thing, we know the switching lemma with parameter square root s. So we know the probability that the degree equals k is at most a constant times p times square root s to the k, right? And under the restriction. Now I want to ask what is the expected size of the restricted function, and I will concentrate. Okay, I will concentrate when p. As we said here, it makes sense to take p to be like 1 over a constant times square root s. So I concentrate over this case, and for this case I want to show that the expected size is O of 1, right? Because if I plug it here, 1 over square root of the size, I should get O of 1. This is like a special case, but I claim that this is the hard case, and everything else is reduced to this case quite easily. So I just want to show you this case. So what is the expected size of the restricted function? So I can take as before. So I'm going over all possible k's from 0 to n. The probability is that the degree equals k. Times the expected size, condition on that. Okay. So recall that we said something about Boolean function when the degree equals exactly k. We said that every Fourier coefficient is an integer divided by 2 to the k. Since the sum of square equals 1, it means that I don't have many non-zero Fourier coefficients. I have at most 4 to the k of them. Right? So I can write if I know this, I can write the Fourier expansion of f restricted by rho. And it has a sparse Fourier expansion, and I could write from this Fourier expansion, I could write the formula of size, I don't know, 100 to the k. So I don't really care about the constant here, so I can allow myself some slack. So this was, the Fourier expansion was with 4 to the k terms, and I can write quite easily for meta De Morgan formula of this size.
Right, it's not clear it's the Morgan. It's like
right.
polynomial. You have to.
Yeah, so I need to do. So, for example, I can write a formula for majority, and then, yeah, but it requires a little bit of work, but something like half a page, okay, not more than that. Yeah.
It's not written already in this form. You have to.
Yes.
Convert to the
Yeah.
notation.
Yes.
It's written like polynomial.
Exactly. Yeah. So now I can pick this constant to be big enough. So this will be like 1 over 200 to the k. Right? And then I get that this is O of 1. Okay, so yeah, so we done most of the hard work before that.
I don't know if you mentioned, I don't remember the first part. So it all starts with this lower bound, which is, it gives the lower bound on parity, and actually it gives the best Avishay paper and Aspas paper. This implies lower bounds on the size of explicit functions in P for this type of model, which is n cubed. And all this follows from an upper bound of quantum query complexity.
Yes.
So an upper bound, the right-hand result, proving that formulas of size S require only square root S queries in quantum algorithms. This upper bound implies lower bounds.
Yes. Yeah. And we see also relations on the other end. For example, this lower bound imply constructions, for example, pseudo-random generators. And yeah, so there are a lot of interplay between algorithms and lower bounds.
But the upper bound is quite complicated. The quantum
Yes, I agree.
The upper bound was open for like 10 years and was known for very, very specific type of formulas. And it's a vast generalization of the Grover search algorithm that says that just the OR function on n bits is a square root n query quantum algorithm.
Yes.
Takes OR into any formula whatsoever.
Yes. Yeah, you can interpret this that you could look for a needle in a haystack with time, which is square root of the size of the haystack, right? The Grover algorithm. And the generalization is for any formulas of sizes. Yeah. So the special case that Avi mentioned is that you have just ORs, maybe like a complete tree of ORs. And then you have x1, x2, to xn. So Grover showed that you have a quantum algorithm with square root n queries, and this implies that you have exponentially small Fourier-tails with square root n for this formula. But for all formulas, this was proven by a long line of work. Yes. Okay. So I have time for one more thing, I think. Yeah, so I want to give you a little hint to how some of these results were proven. So I want to talk about switching lemmas, and I will describe it in a high level, and maybe I will give an example for the DNFs. So recall that we want to prove the switching lemma. Okay, which has something like this. However, I want to change things a little bit. Instead of looking at p random restriction where each variable is capital I with probability p, I want to keep exactly L variables alive. Okay, so I take some parameter L and think of L is equal to n times p. And I want to look at, so now I'm denoting by the set of restrictions that keep exactly L variables alive as RL. And I ask what is the probability that the degree is at least k. I want to show that this is smaller or equal than some constant times p times t to the k. Sorry. So p is This is L over N. This is what I want to show you how to prove such a thing. So first, let's define the bed restriction as simply the restriction for which this condition holds. So these are all restrictions such that the degree is big. Right? So the general way to prove this kind of result is, well, okay, so there are two methods. One was introduced by Hastad, which involved
By Yao.
so yeah, okay. Yeah, it was introduced by Yao and used by Hastad in his seminal work. And this uses conditioning by induction. And another method of proof, which I think is a bit easier, is by Razborov. And this is using an encoding. Okay, so what do we need to do? We need to map. We want to say that there aren't many beds. So one way to do it is to map the beds into some set which is small, and to show that this mapping is bijective. Okay, so we are mapping it to restrictions that keep L minus k variables alive. And in order to make it bijective, we need to add some other. Okay, so we take the Cartesian product with some finite set. And the size of this finite set should be O of t to the k. So if we know this, and we know that this is 1-to-1, it tells us that the number of beds is at most the number of restriction keeping k variables alive times O of t to the k. Right? And the probability to sample a bed when I'm going over a random restriction keeping L variables alive, the probability of hitting a bad restriction is exactly this, right? Because just a uniform distribution of all restrictions keeping L variables alive. And what is important? It is important that this number is much smaller than this number, right? Keeping less variable alive, there are much fewer possibilities for this. Okay, so this is roughly, this is n to the L minus k times 2 to the n minus L minus k. Right, I need to choose which coordinates are keeping alive and assign values to the rest. And this is more or less this thing, okay? L over n to the k times O of t to the k. So this is a general way to prove such a thing. And now maybe let's see how it is done for DNFs. But I will take a slightly simpler case. I will take the case where k equals 1. Okay, I just want to show.
The whole cleverness goes into the bijection.
Yes. So yeah, just to define such a map, it's not really difficult, but you need to show that you can decode from the new restriction and the extra additional information, that you can decode the original restriction. So let's show that for width W DNFs, a probability that, okay, so now we are sampling something like this. So we want to show that the probability that the degree is at least 1 is at most O of L over N times W. Okay, so K is 1 here. So we didn't take. Yeah, so what will be.
In expectation, it makes sense.
In expectation?
Well, I mean, you are leaving.
You mean moving from here to the p-random restriction? Or?
Just the idea. If you want this probability to be smaller than 1, so
Yeah.
you would probably pick L to be about N over W.
Yes.
A bit less than N over W. So you are picking a random restriction so that you expect to leave less than one variable alive per clause.
Yes.
And this somehow is enough.
Yes. So this is, I think, is a very, okay, maybe for this case is a little bit simple to prove, but this is very remarkable because there is no dependency on the number of clauses, just on the width. So let's see how this encoding goes. So we have terms, right? We have the first term. So we have ends of some things, or the second term. We have some variables here, xa1. Maybe some are negated. Okay, this is how the formula looks, the DNF looks. Now we apply random restriction, so we are leaving L variables alive. So we check to see what happens when the restriction is bad. When the restriction is bad, it means that this thing is still not determined. Right? It is not a constant under the restriction. So in particular, we could look at it term by term. So each term shouldn't be equivalent to 1, because if it was 1, then the entire thing would be a constant, right? So we start. We look at the first one. So maybe some of these bits were fixed. So this was fixed to true, but this was fixed to, but this literal was fixed to false. So maybe this entire clause is equivalent to false. Okay, so this means that we don't want to look at it. So we look at the next one. We look if it is equivalent to false. If it is, we continue until we reach some ti, which is not equivalent to false, meaning that I can still satisfy it. And we look at the first one according to some order that we do on the terms. And now, since we know that it is still not false, that it is not false and still not true, because if it was true, then the entire thing would be a constant. It means that there is some variable here that is still unset. So what do? We set this variable in order to satisfy the literal. So if it appears like this, we set it to 1. If it appears with negation, we set it to 0. Okay, so and we get from rho, we get, if rho was bad, we get a new restriction, rho prime, that fixes one more variable. Which variable? This one, this guy. But however, now we want to decode, so we need to have some additional information. So what do we keep in addition? We keep the index of this variable in this term. Okay, so this is a number between. This is a number. I don't know. This is some number I between 1 and W. Okay, so in this mapping, this set X will be of size exactly W. Okay, so we are mapping a restriction to a restriction fixing one more variable, and we're keeping the number between 1 and W. And now when we want to decode, so we need to somehow identify that we fix this variable and make it free again, make it a star again. So how do we do it? We again look at these terms, and we look at the first term, which is not equivalent to false. All these terms are equivalent to false, right? Then we didn't change this fact by fixing another variable. However, this term is not equivalent to false because we picked it and then we set this thing to satisfy it. So we identify this the correct term. And since we kept the number of this variable, so there are many variables here. All of them are satisfied. All the variables that are set are satisfied. But because we kept this index, we know which variable we set. So we can make it, so if it was after row prime, it was 1. So now we can return it to be star again. So we can decode, and this proves this thing. And to do it with k things, it's a little bit more complicated, but this idea is more or less what is done. And this is, I think this is nice because it is like programming in some sense. You need to come up with some kind of algorithm and then a decoding algorithm. And once you proved it, you have this switching lemma result. Okay, so thank you very much, and that's all.